This time, let us talk about the antiderivative. We're not going to talk about the derivative anymore, actually. The rest of the course is going to be about the antiderivative, which is a different thing. It's similar. It has a similar idea to it, but it's different the way that you do it. It turns out for various reasons to be slightly harder to do, but anyway, consider this an opportunity to have sort of a clean slate. If you sort of got lost in the previous sections a little bit, this will be a new thing. Everything will be fine. The antiderivative is about doing the derivative backwards. You know, usually I give you a function and say, what is the derivative of this function? This is the other way around. Questions like 3x squared is the derivative of what? That's the kind of a thing that the antiderivative is about. Can you say the answer here? It's x cubed, right? So the antiderivative is all about this sort of inverse kind of problem. If you start with some function which you imagine as being the derivative, what is the thing that this is the derivative of? All right, 3x squared is the derivative of x cubed is the answer. I guess this isn't really a question, right? It's a statement. I'm making a statement here, okay? In this situation, we say 3x squared is the derivative of x cubed. Say, if we say this in terms of antiderivatives, what this means is the antiderivative of 3x squared is x cubed. All right, the antiderivative of 3x squared is x cubed. That's what the antiderivative means. It's a function. So that other function, when you take the derivative, you get the thing that you're talking about. The antiderivative of 3x squared. Actually, I said the here, but you should think, is that the only function whose derivative is 3x squared, right? 3x squared is the derivative of x cubed, but could it be the derivative of anything else? Actually, it could be. This is not the only function whose derivative is equal to 3x squared. Can you think of another one? How about this? X cubed plus 1. The derivative of x cubed plus 1 is also 3x squared, isn't it? So the derivative of the antiderivative of 3x squared is x cubed, also x cubed plus 1. It's because if you were to take the derivative here, you would get 0. The 1 would disappear, and you'd get 3x squared also. Or, you know, there's nothing special about the number 1 there, right? X cubed plus 7. It doesn't matter. Just plus anything. Actually, anything like x cubed plus c, all right, for where the c could be any constant. This is going to be sort of a nuisance. It's annoying to remember this, but actually every time you ever find the antiderivative of anything, it's always going to have this extra plus c in it. That's because no matter what this constant is, it's going to disappear when you take the derivative. All right, this is called the integration constant, the plus c. It usually doesn't matter, but you should put it in your answer when you're doing antiderivatives. So there's a notation for this. What we just said is antiderivative of 3x squared is x cubed plus c, where the c could be any constant. All right, there's actually a way that we're going to write this without using these words. It looks like this. Oh, come on now. 3x squared dx equals x cubed plus c. All right, this thing right here is called the integral sign, and it means the antiderivative. Actually, the integral sign together with the dx means antiderivative. All right, it's a little weird that the antiderivative actually has kind of these two parts to the notation. There's the integral sign, and then you write your function, and then you always write dx. X refers to the fact that I'm doing the antiderivative where the variable is called x. All right. Sometimes you'll see a dt if your function uses a t or whatever. All right. So this thing here and the dx refers to the antiderivative. And after you find the antiderivative, which in this case is x cubed plus c, you don't write the integral sign over here because this is the answer. It's a function, right? The integral sign means the antiderivative of that thing. All right? This is how we write the integral sign. It's pretty cool looking, I think. You know, show off to your friends. They will think you're doing something really awesome. Let's try some other examples, all right? So far, we haven't really talked about how to do this in general. We're just sort of kind of guessing the answers, but we can do a few more just by guessing, right? What is, let's say, integral of 2x dx? What do you say? As you've noticed, sometimes I'm just going to say integral. The antiderivative is also known as this. So this antiderivative, the integral sign, this is also known as the indefinite integral, right? It's called the indefinite integral. There is such a thing as a definite integral, which we're going to talk about soon enough, but this is not the definite integral. This is the indefinite integral. And the answer is another function with a plus c on it. That function has the property that the derivative is 2x. Do you know of such a function? Yes, you do. It's x squared plus c. All right? What about this? What if it was 3x instead of 2x? I'll be a little tricky about this one. What function do you need over here to make it so that the derivative is 3x? Well, you need to, this is a little weirder. Here, remember what happens when you take the derivative. The 2 comes down front, and you get the 2 there, and then the 2 upstairs turns into 1, so you get the x there. This time I want something to happen so that I still get x to the 1, but it ends up being 3 on the top. Well, it has to be x squared so that when I take the derivative, I get something like x, but this is going to make 2x. I want instead 3x. The trick to do that is like so. How do you like that? Now when the 2 comes down, it multiplies onto 3 halves, and it becomes 3 on the front, which is right there. All right, so this is the antiderivative of that. That's a little more complicated, although it shouldn't be too much of a surprise that there's actually sort of a general formula that you can do for integrals of things like that. Is there something like the power rule for antiderivatives? You bet there is. Can you say, generally speaking, if I take the antiderivative of x to the n dx, what is it going to be? You can say, actually, it's like the power rule for the derivative. Remember that the derivative power rule says if you were to take the derivative, you would multiply the exponent in the front and then decrease the exponent by 1. You have to reverse that process. The original process was multiply the exponent on the front and then decrease the exponent by 1. The opposite of that would be increase the exponent by 1 and then divide by the exponent on the front. It looks like this. As always, the plus c goes there. All right. You increase the exponent by 1, and then you divide by the new exponent. Okay. This is the opposite process from doing the derivative, which consists of reducing or multiplying the exponent and then reducing it. You increase it and then divide by the exponent. All right. This is the power rule for the antiderivative, and it works great just the way that the power rule for the derivative works. I would say you have to memorize this, but you're going to do it all the time over and over again, so you won't ever have to really, sit down and try to memorize it, because it's such a basic rule for the antiderivative. Okay. Let me just say this, just like the power rule for the derivative, this works for any n, not just whole numbers. It works for fractions. It also works for negative values of n. Although, when you look at this formula, you will realize there's one value of n for which this cannot work. This works for all n that are not equal to -1. What's the problem with n equal -1? The problem is if you were to try and do this when the n was a -1, you would end up with a 1 over 0 right here. And so this formula cannot be valid because 1 over 0 doesn't mean anything. So this formula works for all n's which are not -1. When the n is a -1, there's a special formula. So what about that other situation? Integral x to the -1 dx, the antiderivative of x to the -1. Well, you can't use this formula. There must be some answer, though. We should just think about what the answer is. Another way of writing that would be 1 over x dx, right? Can you think of any function? Have you ever heard of a function whose derivative is 1 over x? That's what I'm asking. The antiderivative of 1 over x means what is the function whose derivative is 1 over x? There is such a function. It is the natural log of x. I hope you remember that. That was one of our things we talked about. The derivative of natural log of x is 1 over x. Actually, the full formula or the full rule was the derivative of the natural log of the absolute value of x is 1 over x. So typically when you see this written, it's written like this. Antiderivative, or the integral of 1 over x dx, is natural log of absolute value of x plus c. All right, this one, sorry about my, come on, squeaks. This one also you need to have memorized, all right? So this one works whenever the n is not -1. In that special case, when the n is -1, you got to do this one down here, all right? Two more basic properties about the antiderivative, and then we'll be ready to do some examples. Remember these rules for the derivative? The derivative of two things added together is you just do the derivative of each of those two things and then add the derivatives together. And also the derivative of a constant times something, you can just use the same constant and then take the derivative of whatever it was. These are so basic rules, you've been using them all along, but you may have forgotten about them because they're so basic. This is how, for example, the derivative of x cubed plus 8x is actually equal to 3x squared plus 8. And how did I get that? I just did the derivative of this one first, which is 3x squared, and then I added to the derivative of this one, which is 8. I used this rule here. You do this just naturally, sort of in your head without even thinking about it. That's how basic these properties are. The same properties hold for the antiderivative. If the derivative of the sum is equal to the sum of the derivatives, then automatically the reverse should be true. The function whose derivative is a sum should equal the sum of functions whose derivative is whatever, right? The same rule is true for the antiderivative. So this is a rule which is very important, although it's so important that perhaps you will do it just naturally without even thinking about it. If you have two functions added together inside of an integral, the antiderivative is equal to the integral of the first function plus the integral of the second function. All right? And similarly for multiplying by constants. So a constant times f of x dx, the antiderivative is equal to, you can pull the constant out of the integral sign, k integral f of x dx, like so. All right? These two are extremely important. I suppose you should remember these, but like I said, you do them automatically. I'm just telling you so that you can feel good about doing these properties automatically. You don't have to worry about splitting an integral up. If it's added together, you can split the integral. And if there's a multiplied constant on the inside, you can pull the constant out. Pretty awesome. One more thing we should probably talk about, although it's not too complicated, but it comes up a lot. What is the integral of just a constant, like, say, the integral of 7 dx? Well, what is it? The integral of just a constant would be, I want a function whose derivative is equal to 7. That would be 7 times x, and then plus c. So whenever you have a constant integral of just a constant dx, the answer is kx plus c. All right? Again, this is worth memorizing, but you're going to do it over and over again, so you probably won't have to. Another thing that will be a little weird, what if you ever see just this, integral dx? What is that? There's like nothing in there. Well, you can imagine that there's a 1 in there, 1 times dx, a constant 1. And so if you use the k as a constant, then the answer is just x plus c. This looks a little weird, but that's how you interpret integral sign with just a dx, as if there was just a 1 in there, and you get 1x plus c. Let's do some examples. A few examples here. Are you ready for this? How about this? Integral of x squared plus x minus 4 dx. All right? I want to do the antiderivative of this thing. First of all, I have several things added together. So by that rule about the integral of things added together is you add together the integral. So I can do it like this. This is the integral of x squared dx plus the integral of x dx. I should have put parentheses up here. Everything here is inside the integral. Minus the integral of 4 dx. I didn't actually say, but you can split up integrals across a minus sign too. It's not just for pluses, it's for minus also. All right, and now we go down the line and do each of these integrals. The integral of x squared, each time here I'm going to use the power rule. You increase the exponent by 1, so it becomes x cubed, and then you divide by the new exponent, so it becomes 1 over 3 x cubed. All right, over here, there I don't see an exponent, but I imagine the exponent is 1 here. So the exponent becomes a 2, and then I divide by the new exponent, and I get 1/2 x squared. And the final one, 4 dx. What is the antiderivative of 4? Remember, the integral of a constant is that constant times x. So the answer is 4x. And then I put my old plus c at the end. Here, technically, I had 3 different integrals, and each one of them should have its own constant, but the convention is to just sort of gather all of those constants together. Whatever those 3 constants were, they add up to yet another constant, so you might as well just say plus some other constant over here. All right, this is how we do it. Now, I sort of did a couple steps here. Ordinarily, though, when you're doing this, once you know what you're doing, I expect you to be able to just go from here to here in one step. You just go down the line here. You say, okay, x squared turns into 1/3 x cubed. The x turns into 1/2 x squared. The 4 turns into 4x. And I'll put the plus c, and that's all there is to it. All right. Antiderivatives of polynomials are pretty easy. I should say, like, they are easy. They're really easy. You just do that. There's a few times when you have to do a little bit of work for it. Let's do some more complicated things. How about this? X plus 1 over x squared times dx. I want the integral of that thing. You got to resist the urge. You might feel like, oh, can I just like do the antiderivative of everything upstairs and then do the antiderivative of everything downstairs? The answer is no, you cannot do that. You have to somehow rewrite this fraction so that it looks like something that you do know how to take the antiderivative of. And there's several ways that you could do this. Here's how I'm going to do it. I'm going to rewrite, instead of over x squared, I'm going to write it as x plus 1 times x to the minus 2. Because x to the minus 2 means 1 over x squared. All right. Why did I do that? Now I'm going to distribute here. Integral. So when you distribute, you're going to add exponents. This is x to the 1 times x to the minus 2 becomes x to the minus 1. And then plus x to the minus 2. That's, you distribute there. The x. All right. And now it looks more like a polynomial. Now we can just do the antiderivative in each position. And what do we get? What is the antiderivative of x to the minus 1? Remember, this was the special rule. That is natural log of absolute value x. The antiderivative of x to the minus 2, you do the power rule. So it's going to be the exponent increases. Negative 2 plus 1 is negative 1. And then I divide by the new exponent, like so. And as always, I put plus c. All right. So this is how you can handle some types of fractions, but this trick doesn't always work. It will work if you have something divided by a power of x, but actually if the fraction were the other way around, if it was x squared over x plus 1, you're completely screwed in this case. You can't do anything like that. And actually, we're not even going to talk about how to do this. This one is much harder to take the antiderivative of. Okay, so far we've talked about mostly just powers of x. What about exponential functions, antiderivative of e to the x? You got to imagine and ask yourself, what is a function whose derivative is equal to e to the x? Well, the answer is easy. It is e to the x. That's the whole, like, that's what's so great about e to the x, is the derivative of e to the x is e to the x. So automatically it's true the antiderivative of e to the x is e to the x plus c. That's just the technicality. All right, there's a variation on this which is actually going to be very useful. What if you have a constant inside of the exponent there? It turns out the antiderivative of e to the k times x is like this, 1 over k e to the kx plus c. All right. What I'm saying is the derivative of this function is equal to e to the kx. That's what this means. And I hope you agree that it is. When you take, if you were to take the derivative over here, you would get the same function here, but because of the chain rule, you got to multiply by k, and it would cancel the 1 over k, and you would just get e to the kx. All right. So this is the rule for exponential function with an extra constant up top. All right. What if it's not e to the x? There are rules for this also. They look similar. If you remember your formula for the derivative of a to the x, derivative of a to the x was equal to a to the x times ln of a. All right. You can probably guess what this is going to do. It's like this, only backwards. It's this. When you take the derivative, you get the same function again, but you have to multiply by ln a. When you take the antiderivative, you get the same function again, but you have to divide by ln of a. All right. This can be slightly confusing. If you found this formula hard to remember, You will probably be additionally confused by this formula, which is almost but not quite the same, right? It has division instead of multiplication. Anyway, there's one last variation on this which has an extra constant inside the exponent, like so. And the answer for this, it's like a combination of these two formulas. It's 1 over k ln a to the kx plus c. Let's just try a few with those exponential functions. How about this? Integral of 7e to the 2x dx. All right? We just talked about integral of e to the kx is 1 over k e to the kx. What about that 7 there? That wasn't part of those four formulas that I just wrote out there. That's because it's a constant multiple on the inside of the integral, and we can always just pull a constant out of the integral. That was something I said before. So, there's a 2 up there. 7 integral e to the 2x dx. Always a good idea to pull a constant out of the integral. It will make things simpler. And now from here, you just use the formula that I just said. 7 times 1 over 2 e to the 2x dx. Not dx. Come on now. You should not write the dx anymore, because I just did the antiderivative, right? What the dx represents, the integral sign and the dx mean I'm going to take the antiderivative. Having done the antiderivative, you don't write them anymore because I did the antiderivative, all right? You might find yourself wondering, what about the dx? How come the dx disappeared? Well, it disappeared for the same reason that the integral sign disappeared, because you actually did the integral, so you shouldn't write the integral sign anymore, right? It's kind of like, 3 plus 4 equals 7. So where'd the plus go? How come the plus disappeared? Because I did the plus. The plus is done. I'm not going to write it anymore. It's in the past, right? Over here, the integral sign and the dx both go away because you did the integral. And that's the whole point of them to begin with, was to say you're supposed to be doing the integral. And I did the integral, so they go away. All right. How about, let's just try one or two more. How about 2 to the power negative 2t dt? I'm changing up the variable name just for fun. All right. What's it going to be? Actually, this one fits that old formula, integral a to the kx dx, right? Where the a is 2, the k is negative 2. So just plug into that formula. What do you get? You get 1 over minus 2 ln 2 to the minus 2t plus c. As always, you got the plus c. All right, one more. Okay, this time I'm using a variable named u. E to the 3u plus 7u to the minus 2 du. Take the integral of that, I say. This is not terribly hard, just to demonstrate. Sometimes you can have these things mixed up. This one's an exponential. This one's like a polynomial type function. So you can just do the integral. You use the appropriate formula in each position. Since they're added together, we can just do them separately. The first one then becomes 1/3 e to the 3u. The second one, that was the e to the kx rule. This one, you use the power rule. You increase the exponent by 1, so it becomes u to the minus 1, and then you divide by that new exponent, and this is your answer.